In the last section, we spent a lot of time on coming up with algorithms for computing the LU factorization. But computing the LU factorization in and by itself is not really interesting. Let's see how it actually fits into something that is useful. If you have a square matrix A, and you're trying to solve AX equals Y, then one thing you can do is create an appended system and do Gaussian elimination, etc., etc. The other thing you can do is say, okay, let's take A, let's compute its LU factorization, probably with pivoting, but let's leave that alone. And then we can use that LU factorization to solve the system. How? Well, you know that A is equal to L times U, so you know that this set of equations really can be stated as L times U times X is equal to Y. You can then place some parentheses there, and you can say, well, I don't know what this vector is because I don't know what X is, but I can give it a name. Let's call it Z. And then you get that L times Z is equal to Y. Well, when you get to this point, you know what Y is and you know what L is. Why do you know what L is? Because you've done your LU factorization. And then you can use this to solve for Z. This is now a lower triangular system, and a lower triangular system is easier to solve. And then once you know what Z is, you know that U times X is equal to Z, and you know what U is, and you know what Z is, and therefore you can solve for X. And notice that U is an upper triangular matrix, and solving with an upper triangular matrix is also a lot easier than solving a general system. So what's the point? The point is that in order to do something useful with the LU factorization, we should also derive algorithms for solving with a unit lower triangular matrix and an upper triangular matrix. Now, if you manage to come up with algorithms for computing the LU factorization, you can probably come up with algorithms for computing the solution to triangular systems. And then, of course, you would want to derive multiple algorithms because you would probably want to pick the one that computes with the matrices with columns. And then you add that to your library of routines with which you can now solve linear systems. We actually ran into some of this already before. For example, when we discussed algorithmic variant 1, the one that was derived from loop invariant 1, at some point we had to compute what in the end we stated as A01 becomes L00 inverse times A01. And I made some vague comments about the fact that you really should think of this as the operation that multiplies the inverse times that, as opposed to procedurally inverting the matrix and then multiplying. Now, why is that? Well, that's because you can rewrite this as L00 times, let's call it X0, is equal to A01, where you know what L00 is and what A01 is. From this you can then use the exact same algorithm that you derived here to compute X0. And if you do that in such a way that the result overrides A01, then you will have achieved the net effect of this operation here. Okay, so triangular solve. Now, in that same algorithmic variant, the one that comes from invariant 1, we also ran into the case where A10 transpose had to be updated by A10 transpose times U00 inverse. Well, that gets a little trickier. A row vector should be computed as a row vector times the inverse of a matrix. We can think of that alternatively as trying to find x0 that satisfies this constraint right here, where we know what u00 is, we know what this row vector on the right hand side is. And that's starting to look sort of kind of like solving a triangular system. I should have had a transpose on here because this is a row vector. Well, we can play with this a little bit more. We can say, well, what if we just transpose both sides? Remember that if you multiply and then transpose, that's the same as swapping the order and transposing each part. So what do we get? We get u00 transpose x0 transpose transpose is equal to a10 transpose transpose. Now remember, this here, the transpose, is part of the label we give to that part of the matrix. Here we could actually just say, well, we want to compute this vector, and whether it comes out as a row vector or a column vector doesn't matter. We want to take the result and just overwrite it into the result. But let's go ahead and put the transpose on there. Okay, this now is a column vector. This is now a column vector. What about u00? Well, if you take an upper triangular matrix and you transpose it, you get a lower triangular matrix. So you could go ahead and actually take the matrix, transpose it, and then feed the result into a function very much like the one you created for this. The catch being that this matrix doesn't necessarily have ones on the diagonal, while this here was a unit lower triangular matrix, so you had to change things slightly. Or you can say, well, wait a minute, we don't actually have to explicitly transpose the matrix. We can just compute with it as if it was transposed. And if you start looking at the partition matrix expression for something like this, you can simply come up with algorithms that work with the data where it's already stored without having to explicitly transpose. How can we summarize all of this? Remember that there is this interface called the basic linear algebra subprograms, and one of the operations that it supports is triangular solve. And there it looks at ax is equal to y, overwriting y with the result, where this particular matrix can be lower triangular or upper triangular. It can be optionally transposed. That would give us the ability to solve with this. And you can also indicate whether it's unit or non-unit triangular, which means that if it's unit triangular, then implicitly the entries on the diagonal are equal to 1, and if not, then you actually use the entries that are stored on the diagonal. And you can imagine that you can come up with all of the different algorithms for all of the different cases, where notice you also need to be careful, because while the vector x mathematically here is a column vector, physically it may actually be stored as a row vector. There's a difference between how it's stored and how you view it mathematically. And what does that mean? That means we can come up with lots of different algorithms. You can imagine how many homework exercises I could make from just this problem right here.